This is problem 66 from chapter 12. You have a quiz which is similar to this problem, but pay attention because the numbers in the graph are different for your quiz. We have a boat which is traveling along a straight line with the speed described by the graph. We want to construct the position versus time and the acceleration versus position graphs and determine the time required for the boat to travel a distance of 400 meters if s is equal to 0 when t is equal to 0. So we have the graph here. One thing that you should note is that here they're telling us what the velocity squared is for some reason instead of telling us what the velocity is. So I would rewrite that as the velocity is equal to the square root of 4s, just so we don't forget that was the velocity squared when we go to plug things in. Okay, and then we have velocity versus position, so we're going to use equation 12.3, and we're going to rearrange equation 12.3 like we have done in the past by bringing the ds over to the other side. So we have the acceleration is equal to dv ds times v. So I want to take dv ds for the first part of the graph, so this is going from s is equal to 0 to s is equal to 100 when we have v is equal to the square root of 4s. So the acceleration is equal to dv ds, so that's the derivative with respect to s of the square root of 4s, or maybe it would help if you write that as 4s to the 1/2 power, times the velocity, which is just the square root of 4s. So if we take the derivative of 4s to the 1/2 power with respect to s, we have 1/2 times, then you lower the power, so that would be 4s to the negative 1/2 power, or 1 over the square root of 4s. Oh, and then I'm not done yet, because I have to use the chain rule. I took the derivative of 4s, now I have to take the derivative of what's inside, so the derivative of 4s is 4. Okay, so then this is times 4s. Well then, this is just 1 over the square root of 4s, so that and that cancel, and then you just have 2. So when I draw the acceleration versus position graph, the acceleration is a constant up until I get to 100. So then I have to go from s is equal to 100 meters to s is equal to 400 meters. And for this part of the graph, we have v is equal to 0.2s. Well, we solve it the same way. It's just a little easier now because you're taking the derivative of 0.2s here, and the derivative of 0.2s with respect to s is just 0.2. So that's what we get for the acceleration, which is 0.04s. So this is linear. And notice that, I guess we should look at the graph in the book to see this better, but the slope is not continuous here. So because the slope is not continuous, we have a discontinuous acceleration versus position graph. So we're going to jump up here, and now we have something linear. And you can see that if you take 100 and you put it into, well, you can't really put it into your equation here because it's just a constant. So we're at 2 here, but then if you take 100 and you put it in here, you get 4. So the two functions do not agree at 100 meters, so it's discontinuous there. Okay, so that is the acceleration versus position graph. Now we want position versus time. So we have velocity versus position, but I want position versus time. So I'm going to use this equation here because I have information about velocity and position, and I want information about time. So using equation 12.1, we have v is equal to ds dt. And then as we go from s is equal to 0 to s is equal to 100, we have v is equal to the square root of 4s. So I'm going to put that in for v. And then I have ds dt over here. So to solve, I need to bring the dt over to the other side. So I have, let's call this 2 times s to the 1/2. No, let's call it just 2 times the square root of s. I can't really integrate this way though because I have s on the left-hand side and ds on the right-hand side, so I'm going to bring the square root of s over to the other side. So then I have 2 dt is equal to ds over the square root of s, and now I can integrate. What you have to be careful about here is putting in the limits of integration because we want position as a function of time. So we're going to start at 0 because we're going from 0 to 100. And then your upper limit of integration, because you want position as a function of time, it's just going to be s and t. I think that I will stop here. Your quiz is going to be similar, and I think you should be able to integrate that on your own. So you can finish that on your own. So then we're going to jump ahead and look at the next part as we go from s is equal to 100 to s is equal to 400. For the second part of the graph, we have the velocity is equal to 0.2 times s. So we're going to use this equation again. The velocity is equal to 0.2 times s. And we have a ds dt over here. We're going to flip things around like we did up here. Bring the s over to the one side, bring the dt over to the other side. So now we have 0.2 dt and ds over s. We're going to integrate. But now we're going from 100 to 400, so our lower limit of integration for position is 400. I need the lower limit for the time over here. So I can take the equation, which I'm supposed to have up here, but I skipped solving it. But I'll just tell you what you should get, okay? Because it is going to be different for the quiz. So if you want to check things for this problem, you should have s is equal to t squared. Again, they don't have the same units, but we're not going to put the units in. Okay, so when the position is equal to 100, from our equation here, we get when s is equal to 100, t is equal to 10. So s is equal to 100 meters, t is equal to 10 seconds. So the corresponding time for the lower limit of integration here would be 10, and then our upper limits of integration would be t and s. Okay, then you can go ahead and integrate. On the left-hand side, I'm going to skip some steps here, but you would have 0.2 times t minus 10, and on the right-hand side, you would have the natural log of s over 100. You want position as a function of time, so then you're going to solve this. This is an s. It looks kind of like a 5. You're going to solve this for position. So I'm not going to do all the steps. You can practice that when you do the quiz. But we should have s is equal to 100, and then e to the 0.2 times t minus 100. Then you have to draw the graph. You can use a computer to help you figure out what the graph is going to look like, and if you want to take the equations that you have here and write them on the graph so I know what you were trying to graph, you can do that as well. You also have to find the time required to go 400 meters, so that would be the time that you have here when s is equal to 400. And then finally, you should be able to check the equations that you have. So if you want to make sure that you did the integration correctly, we have the velocity is equal to the derivative of the position with respect to time, and you know what the velocity is supposed to be. So if you go back and you take your equations and you take the, well, let's do this over here. So I have s is equal to t squared. I want to check using v is equal to ds dt. So the derivative of t squared would be 2t. But that doesn't agree with what I have up here because I need velocity as a function of position if I want to check it with what I have here. So we have t squared is equal to s, which means t is equal to the square root of s. So then if I take that and put it in here, I have 2 times the square root of s, which still doesn't agree, but if I take the 2 and put it underneath the square root sign, then I have the square root of 4s. So that works. And then you could also, for the second part, do something similar. We would take the derivative with respect to time of 100e 0.2 t minus 100. And so when I take the derivative here, I just get it at 0.2 times the same thing. And this is equal to s, so that's 0.2 times s. So that works. Okay, and that well, that isn't everything for problem 66 because I didn't find the time required to go 400 meters, but I'm going to save that for you to do.